So a hypothesis is a testable prediction. This is our, you guys might have heard it called an educated guess. At this point, we don't know if the hypothesis is right or wrong, and if we're a good scientist, we don't care if it's right or wrong. We just want to figure out which one it is. If we care too much, we might have a bias, or we might want for it to be right or want for it to be wrong, and then we might have trouble testing objectively. A theory is an explanation of why. So an example would be the theory of relativity, Einstein's theory of relativity. This is an explanation of how the universe works and why it works the way it does based on observations and experimental results. So that's really important. It's an explanation of why and how something works. A scientific law is a prediction of what? It describes a pattern in nature, or it tells us under a certain set of conditions what might happen. So Newton's law of gravitation is a law that predicts the way the planets will move based on all of the bodies of mass in our solar system, or the way that an object will fall towards the Earth based on the mass of the object and the mass of the Earth. So here's the problem. A lot of people that are not scientists use these words improperly. They use the word theory improperly in place of hypothesis. So you guys might have heard someone say, well, I think I have a theory on that, or something similar. And what they mean is, I have a hypothesis. I have an educated guess. I have an idea that we could test. The theory has already been backed up by experimental results and many observations. So we don't start with a theory and guess. And you might have heard people say, oh, this theory, it's just a theory, and it could be wrong. And that's true of actually anything that we talk about. Anything that we have could be wrong, but it's usually not wrong in the way you think, in that it's not usually completely wrong. Let's talk about Newton's law for reference frames. So Newton came up with a way to talk about reference frames and velocity. So let's say that you are standing inside of a train car, and the train car is moving forward at a velocity of 10 meters per second. Newton said that we could consider our reference frame as being inside that train car. So as long as the train car is moving at a constant rate and we're inside of it, we're not going to really feel that we're moving 10 meters per second. And if you have trouble going along with that idea, know that you're moving right now very quickly. You're not moving relative to your desk or your computer. You're not moving relative to the room if you're sitting down, but you are moving very quickly relative to the sun. The Earth is moving very quickly around the sun. So you're in the reference frame of the Earth right now. So we're going to pretend here we're in the reference frame of this train car moving forward at 10 meters per second, and you throw a ball forward at 5 meters per second. So Newton's law for reference frames was that in the reference frame of the train car, the ball is moving 5 meters per second. But in the reference frame of the Earth, outside of the train car, the ball is moving at 10 plus 5 meters per second, or overall, it's traveling faster than the train car at 15 meters per second. And this law worked very well to predict what would happen to objects that were moving inside a reference frame that was moving. So it's a law. It predicts what will happen under a certain set of conditions. It's not explaining why it happens. It's predicting what will happen. So that's a law. But here's the problem. We found out later that there was another, and Einstein came up with this. There was another scenario that didn't work. Remember that Einstein's theory of relativity is based on an idea that nothing can travel faster than the speed of light. So let's say that we get a train car that's traveling 99% the speed of light. So it's not disobeying that rule. It's traveling 99% the speed of light. Now you're in the train car and you throw a ball at 2% the speed of light. According to Newton's law for reference frames, the speed of the ball outside the reference frame of the train car should be 101% the speed of light. It should be going faster than the speed of light. But it turns out it didn't work that way. So scientists used experimental analysis to figure out that the law, the equation that we were using to predict the motion of the object, was incomplete. It wasn't completely wrong. It worked great for small speeds, but as the speeds got larger, the results of the predictions got less and less accurate. And so the equation was modified to include a term that allowed for accurate results at low speeds and accurate results at very, very high speeds. And this is usually what happens. We come up with a scenario where our predictions from the law no longer yield accurate results, and we need to modify the law based on this new scenario that we hadn't considered before. That doesn't mean that the law we had was completely wrong or should be abandoned entirely in every scenario. Now, another thing that people usually get wrong is they have the idea that a theory, when tested and proven, becomes a law. And this is not the case. A theory is different than a law. A theory does not become a law, and a law does not get demoted to a theory if there's a problem with it. And the reason we might think this is only because in our everyday lives we misuse the word theory. A theory is an explanation of why something happens in the universe, and it's based on observations and experimental results. And if we ever get an observation or an experiment that conflicts with our theory, we'll modify the theory. But the theory is formed based on a lot of testing. A law is a prediction of what will happen under a set of given circumstances. So it doesn't explain why, it explains what will happen, and it tries to predict what might happen. In the next chapter, we'll talk about motion, and the laws of motion help us predict what the motion of an object will be if we give it a certain speed and we start it in a different place. So these three words are very important to understand, and I encourage you, if you ever hear someone using these three words wrong, just politely correct them. So that they can kind of understand what the words actually mean. Okay. So again, we talked about this. Theories and laws are well accepted by scientists, but they're not set in stone. Sometimes we encounter new scenarios that help us realize that the theory or law needs to be revised to be more accurate in this new situation. An example of that would be moving from Newton's physics, which was all about motion on the Earth and motion among the planets, in quantum physics, where we want to know how things move on a very, very small subatomic scale. And it turned out that a lot of the theories and laws didn't work very well at that small scale. It didn't mean they were wrong. They just needed to be revised based on this new information. All right, scientific method. So we determine the problem, we research and gather information, we make a hypothesis, our educated guess. We test that hypothesis using some experimental procedure, we analyze the results, and then we draw conclusions. And any good application of the scientific method will repeat these steps over and over again to verify what's going on. One way to test a hypothesis is with an experiment, and we're going to talk about an experiment here real quick. So let's say that we want to set up an experiment that determines which of 3 fertilizers helps a plant to grow the biggest. We need to pause for a second. We need to decide what are other things that might affect the growth of the plant. So sunlight, room temperature, types of soil. If it's not getting any sun, it won't grow. If it's really cold, it won't grow. So we have to isolate these other variables that could affect the outcome that we're interested in, which is, if we're using a fertilizer, we're probably hoping to grow a large plant. So here's an experiment that is set up properly. We identified a bunch of variables that could affect the way the plant grows, and one of them was amount of water. We're not trying to test how the amount of water affects plant growth, so we keep it the same for all of our samples. Amount of sun was the same way, so we keep it the same for all of our samples. Okay, so I'm going to highlight these here real quick. It's not very good. So we're going to keep those 2 variables constant, so they're called constants. Okay, now this is the variable that we're manipulating, the type of fertilizer. So the type of fertilizer is our independent variable. The independent variable is the one variable we're changing during the experiment. The thing that we hope that variable will affect is known as the dependent variable. It depends. And then there's one last key thing down here at the bottom. We always run the test with one sample where we don't do any change to our independent variable, and this is called our control. Very easy to mislead people without a control. Let's say that we just used plants A and B. We used fertilizers A and B. And we see that plant A grows 16 centimeters and plant B grows 14 centimeters. So plant A grows the most of samples A and B. But what if putting no fertilizer in at all yielded 20 centimeters of growth? Then our test would be totally different. It's not that fertilizer A is better, it's that fertilizer A does the least harm. So we always need a control. We need to see what happens when we don't have that variable present. All right, skipping ahead. We talked about each of these slides already. Quickly, we'll talk about being objective. A bias occurs when a scientist expects a change. We need to try not to get the results we want and just look at what the data is telling us. We can also lessen bias by running multiple trials and not just stopping when we get the data we want.